everyone, and welcome to the Algebra 3 Unit 2 test review. This is Mrs. Hubbard, and I'm just going to go ahead and jump in, and we're going to go through these problems to make sure we have a solid understanding of what's happening. While this is a really good review to start with, it's probably not the best thing to end with, so I would make sure that you are also studying your notes, homework, and quizzes from this unit. So first thing we're going to do is write the equation of the quadratic with the given information. It didn't specifically say what forms we needed to use, so we have a little bit of free reign there. But there are some specific forms that are going to help us the most. So starting with the first one, we're given the vertex and a point, and so that vertex is a hint. We're going to use vertex form, which is y equals a times x minus h squared plus k, where our vertex is hk, and the point that we use is going to be x comma y. Okay. So with that being given to us, we can now plug into this formula to solve for a. So we'll say that y, which is negative 10 coming from over here, equals a, we don't know what that is yet, times x, which is a negative 1, minus h, which is a positive 1, but again, remember it's subtraction, squared. We cannot forget that squared. That's what makes something quadratic, so we have to leave that in there. And then plus k, which is 2. From here, we can start solving. So we'll follow PEMDAS rules. So parentheses, so negative 1 minus 1 is a negative 2. Again, keep that squared there. That's what makes something a quadratic. And negative 2 squared, negative 2 times negative 2 is going to give us a positive 4a. And now it's a pretty simple equation from here. So we'd subtract 2 from both sides to get negative 12 equals 4a, and divide both sides by 4 to get that a equals negative 3. So now we have that leading coefficient and our vertex, so we can go back to this form and write our final equation, which will be y equals a, which we just found to be negative 3, x minus h, which is still 1, squared, again, need that squared in order for it to be a quadratic, plus k, which is still 2. And so this would be our equation for that problem. And that's how we go about solving it. Now, B, it doesn't give us the vertex, but it gives us some zeros and some points. So that is a hint when we have zeros like that, that instead of using our vertex form, we're going to use our intercept form, where this is P and this is Q. So remember, our intercept form is y equals a times x minus p, x minus q. And again, this point is going to be x comma y. Change colors real quick. So again, we can plug all this in. So we'll say y, which is 3, equals a, that's what we're trying to find, times x, which is a negative 3, minus p, which is a negative 2. So that double negative there is going to end up going positive, times x, which is still negative 3, minus q, which in this case is a positive 3. And so that would be our setup there. So now again, we need to follow our PEMDAS rules. So parentheses, so negative 3 plus 2 is a negative 1. Negative 3 minus 3 is a negative 6. Negative 1 times negative 6 is a positive 6a. And then we would divide both sides by 6. Hopefully we know that 3 divided by 6 will actually reduce down to 1/2. From there, we have our leading coefficient. And again, we can go back to that original equation and write our final solution. So we'd say y equals a, which we just found to be 1/2, x minus p, which again is a negative 2. So yet again, that double negative is going to end up going positive, times x minus q, which will just stay negative because there's not a double negative there. And so this would be our solution. Please note that when we're writing an equation for these, we should have both an x and a y in our final solution because it's an equation. And so those are our answers for those two. Moving on. Now we're going to factor each expression. And we always want to check for the greatest common factor first. So the first thing we look at in this first problem is there any number and or variable I can take out of all three of these? Yeah, 6, 34, and 20 are all going to be divisible by 2. So I can take out a 2. And they also all have at least one x to the first attached to them. So I can also take out an x. So 6x to the third divided by 2x is going to leave us with 3x squared. 34x squared divided by 2x is going to leave us with 17x. And 20x divided by 2x will give us plus 10x. I'm sorry, plus just a regular 10, right? Because we pulled out that x. Okay, so I'm going to leave that 2x out front. That is a factor, and I cannot just get rid of it. But now I have 3 terms, and so that's a hint that I'm going to end up doing my box method here. So in my upper left-hand corner, I'll put the squared term. In my bottom right-hand corner, I'll put the constant. I'll multiply those two together. So I want something that's going to multiply to 30x squared, but I want it to add to that middle term of 17x. So the two numbers that would do that are going to be 15x and 2x, right? 15 times 2 gives 15x times 2x gives us a positive 30x squared. 15x plus 2x gives us a positive 17. Then I look at the greatest common factors in each pair. So between 3x squared and 15x, I can take out a 3x. Between 2x and 10, I can take out a positive 2. Between 3x squared and 2x, I can only take out an x out of both of those. It's the only common factor they have. And then out of 15x and 10, both of those are divisible by 5. So this will factor. We'll keep that 2x out front, right? 3x plus 2, x plus 5. And because this did not say to factor and solve, then that would be our final answer, and we can just stop right there. Okay, moving on to the next one. Okay, so maybe if you're really good at being able to pick out these perfect square combos, you might be able to look at this and say it's x minus 5 squared, and that would be totally fine. If you didn't see that, then we should again see that we have a trinomial here. First thing we always check is that we are going to see if there's a GCF. So looking at all three of these, none of them have a coefficient or a variable in common. So that's a hint that we're going to do the box with those 3 terms. Okay, we'll put our squared term in the top left, our constant in the bottom right. We'll multiply those two together. So we want something that multiplies to a 25x squared, but adds to a negative 10x. So the two numbers that are going to do that are negative 5x and a negative 5x. Out of x squared and 5x, I can take out an x. Out of negative 5x and 25. So because that x term is constant, because that x term is negative, I am taking out a negative number. I want my x's to be positive if possible. So I'm going to pull that negative out, and both of these have a 5 in common. Out of x squared and negative 5x, I can only take out an x. And out of negative 5x and 25, again, that negative 5x is negative, so I'm going to pull out a negative 5. And then we do want to double check ourselves to make sure that these are multiplying correctly, whether we needed to pull out a negative or a positive. And then we're going to write this out. So if I wrote it, it would be x minus 5 times x minus 5. But remember, when we write something twice, it's really just that factor squared. So that's my answer. Okay, next one. We have 4x squared minus 36. Again, first thing we want to check is to see if it has a greatest common factor. Well, out of 4x squared and out of 36, I can take out a 4. So I'm going to go ahead and do that. And I'll be left with x squared minus 9. Then we have to check to see if it factors further. And in this case, it actually does. Then x squared minus 9, because I have a squared term and another number, whether it's a perfect square or not, it's going to factor because it's split by subtraction. So the square root of x squared is x. The square root of 9 is 3. So I would say x plus 3, x minus 3. Because whenever we have, remember, a squared minus b squared, that factors to a plus b, a minus b. So you need to take the square root of both of those and then add them together and subtract them. Again, this only works when we are dealing with a difference of squares, which means we have to have them split by a subtraction symbol. And so that would be our final answer, and we would keep that GCF out front. Okay, looking at D, we should check to see if it has a greatest common factor. Okay, out of 2, -11, and 6, we can't take anything out. There's no variables in common, and it's 3 terms, which is, again, a hint we're going to use our box. So that would give me 2x squared here, -6 here. I'll multiply those two together. So I want something that multiplies to a -12x squared, but adds to a -11x. Hopefully we should see that that's going to be a -12x and a +1x, or just positive x. It doesn't really matter. Either way is the same. So 1x and x are the same thing. So out of the top two, we can take out a 2 out of both of these, as well as an x. Out of the bottom two, they don't really have any numbers in common, and that x is already positive, so we're just going to keep that as a +1. Out of the left two, I can only take out an x out of that. And out of the right two, that x term is negative, so I'm taking out a negative number, and both of them have a 6 in common. So this would factor to 2x plus 1, x minus 6. And that would be my answer. And that's my answer, and I'm done because I don't have any squared terms left. I can't factor any further, and I'm not solving. Okay. And so that's how we would factor those. So now we are solving the equations, but this time we're doing it by new parent function. So starting with this first one, the first thing we always have to do whenever we're solving is we have to get set equal to 0. So we'll say 3x squared minus 12x plus 4 equals 0. Because I'm solving by new parent function, I'm going to look at the first two terms, and I'm going to figure out what I can take out of it. Hopefully we should notice that we can take out a 3 as well as an x, and that would leave me with x minus 4. I'll keep that plus 4 tacked on to the end because I'm going to need that in a second, but for right now I don't. Now I'm going to look at the new parent function. So that's this piece right here, and I want to determine from that piece my axis of symmetry. So I'm going to say x equals, and I need my 2 zeros in order to determine my axis of symmetry. So the 0 coming from here is 0, and the 0 coming from this factor is going to be a +4, right? Because we set each of those equal to 0 and solve. And remember, whenever we're working in this vertex form, we divide by 2. So we add those two together and divide them by 2, and we'll get that our axis of symmetry is 4/2, which is just a regular 2. Okay, we also need to remember that that is the x value of our vertex. So we just found the x value of our vertex, and now we want to find the y value. So to find the y value, we have to plug that x value back in. So we do 3 times 2 minus 4 plus 4. This time it's not going to be equal to 0 because we're actually solving it. But we're going to go ahead and simplify this. So 3 times 2 times -2 plus 4. 3 times 2 is 6, times a -2 is a -12, plus 4 is going to be a -8. So our vertex is 2, -8. Now we have a vertex and a leading coefficient. So we can actually write this in that vertex form, this y equals a times x minus h squared plus k. So we'll say y equals a, that's the leading coefficient, so that's going to be 3, times x minus h, which is the x value of our vertex, so that's 2 squared, plus k, which is the y value of our vertex, so that's going to be a -8. So it's actually going to be -8. But we're not set equal to y here. We're set equal to 0. And now we need to solve. So in order to solve this, the first thing we're going to do is we want to get rid of this 3 in front of the squared so that we can take a difference of squares. So we'll divide absolutely everything by 3. So that'll give us that 0 equals, these 3's will cancel, leaving us with x minus 2 squared minus 8/3. Okay, and now we're going to factor it because technically speaking, we have a difference of squareds here, right? We have a square here, and we'll just take the square root of this. So remember, whenever we factor this, we do the square root of the first term. So x minus 2 plus the square root of the second. And x minus 2 minus the square root of the second. So those would be our factors. From there, we'll take each of those and we'll set them equal to 0 and solve. Okay. So what I mean when we solve, and I'm going to do this in just kind of one step, we'll have to add 2 to both sides and subtract radical 8/3 from both sides. So we'll get that x equals 2 minus radical 8/3 from this first factor. And for this second one, we'd have to add 2 to both sides and add 8, the square root of 8/3. And so we'll get that x equals 2 plus square root of 8/3. If we could, we would simplify that denominator, but sadly it doesn't simplify. You also could have written this as 2 plus or minus the square root of 8/3. Just make sure that that square root covers both the 8 as well as the 3. And so that would be our answer. The second one is a little bit easier because we don't have that leading coefficient, so we don't have to worry about that division part. Or well, we do have a leading coefficient, but it's just 1, so that does make it a little bit simpler on us. However, we do start the same way. So we look at the first 2 terms and we ask, what can I take out of that? So out of this one, we can only take an x. So we'll say x times x plus 10 minus 3 equals 0. Again, we want to find that axis of symmetry. So we'll say x equals the 0 from this piece, which is 0, plus a 0 from this piece, which will be -10 divided by 2. Okay, right, and I'm getting those zeros by setting each one of those factors equal to 0 and solving. So that's going to be -10/2, which is just a -5. Again, that value is the same as the x value of my vertex. So to find the y value of that vertex, I'm going to plug back in. So -5 times -5 plus 10 minus 3. We'll do PEMDAS. So parentheses gives us a 5 here. -5 times 5 is a -25 minus 3 is going to be a -28. Okay. And again, we're going to go back to that vertex form. But this time our a, our leading coefficient, is just 1. So I'm going to write this as 0 equals x minus h. So minus a -5. That double negative will go positive, squared. Again, we need that because we're working with quadratics. Plus k, which in this case is a -28. Yet again, we have a difference of squares. So we can go ahead and factor and solve that. So we'll take the square root of the first, which will just be x plus 5, plus the square root of the second, so radical 28. And then we'll take the square root of first, so x plus 5 minus the square root of the second, radical 28. Please make sure you're square rooting both pieces. Okay, but I also want to talk really quick about this radical 28, because an important part of factoring and solving and new parent functions and radicals is simplifying. So we want to take this radical 28 and simplify it if we can. So for those who are really good at picking out numbers, we can see that 28 simplifies to 4 and 7. The square root of 4 is 2. Square root of 7 is radical 7, so this will simplify to 2 radical 7. If you struggle with that, the lowest prime that 28 is divisible by is 2, which would give you 14 if you did 28 divided by 2. The lowest prime of 14 is also 2, and 14 divided by 2 is 7. The lowest prime that 7 is divisible by is just 7, and that would leave us with a 1 on top. So this is called the birthday cake method because we get a candle. And then couples come out, and they come out as a pair, and singles stay home under the radical. Either way you want to solve it is fine, but we do want to get into the habit of simplifying these. So this would become x plus 5. I'm actually just going to erase this piece. Plus 2 radical 7. X plus 5 minus 2 radical 7. Now that we've simplified that, we can set each of these equal to 0 and we can solve. So we'll subtract 5 from each side and 2 radical 7 to get that x equals negative 5 minus 2 radical 7. Then we can subtract 5 from each side and add 2 radical 7 to get that x equals a negative 5 plus 2 radical 7. Again, if you can jump from the factored form to your answer, I'm okay with that, but just make sure that you are being careful to get your positives and negatives correct there, because that could really mess up your answer. Okay. Now we're going to solve the quadratic equation using the method of your choice. Not all will factor. Okay. So let's get started on A. So what we always kind of want to check first is we want to see if it will factor, because if it will, that'll save us a heck of a lot of time. So we check a GCF. We don't have any here. Okay. So now let's try our box method. So that would give us 2x squared in the upper left, 7 in the bottom right. 2x squared times 7 is 14x squared. And we want something that's going to add to a negative 4x. Well, the factors of 14 are 1 and 14 and 2 and 7. And 2 and 7 are not going to add to a negative 4x. So sadly, this method is actually not going to work out for us. It's not going to factor nicely. So when it doesn't factor nicely like that, that means we have to go back to that new parent function. So we look at our first two terms, and out of both of those, we can take out a 2x. Please note that when we take out a 2x, we'll be left with x minus 2 rather than 4, right? Because you took out a 2x. Okay. So now we want to find the zeros. So we have from right here, we want to find the axis of symmetry using the zeros. So the 0 from this factor is just 0. The 0 from this factor would be a positive 2, right? Because you'd set that equal to 0 and solve. And so our axis of symmetry will be 1. Again, that is the x value of our vertex. And we'll plug it back in to get that y value. So we'll say 2 times 1 minus 2 plus 7. It'll be 2 times 1 times a negative 1. Okay, so this will be negative 2 plus 7, which is a positive 5. From here, we're going to rewrite this equation in vertex form. So we would say we would say x minus 1, x minus h squared plus k, which is 5. And then the only other thing we need to make sure we look at is if we have a leading coefficient, which we do. So we'll have to put that 2 out front to take care of that. From here, we should be able to solve. So we'll divide everything by 2 because we want to get that squared alone before we can factor and solve. So that'll give us, these 2's will cancel, giving us x minus 1 squared plus 5 over 2 is equal to 0. Okay, so now we run into a slight problem, and that's coming from the fact that this is split by addition rather than being split by subtraction. So when it's split by subtraction, we can do difference of squares and the world is a pretty place. However, when it's split by addition, we can still do difference of squares, but this time we're going to be working with imaginary numbers. Because if I want to make this a difference, instead of a positive 5 halves, I would have to make this a negative 5 halves. Okay, so I would say x minus 1 plus, or I'm sorry, x minus 1 plus the square root of a negative 5 halves, times x minus 1 minus the square root of a negative 5 halves. Okay, and let's talk about what that would simplify to super quick. So hopefully we should remember that whenever I have a negative under the radical, what I can do with that is I can take out an imaginary number, right? Because a negative under the radical means it's imaginary. That's not possible in the real world. So I take out that I, and then I would just leave the radical and the fraction the way it was before. I can't simplify radical 5 the same way I can't simplify radical 2. So the only way I can simplify this is by taking out an I. So I would get x minus 1 plus I radical 5 over 2, x minus 1 minus I radical 5 over 2. I set that equal to 0, and I solve each of those. Okay, and I know I've been showing how to solve these this entire way, but I'm hoping that we know how to solve fairly simple equations. So from this first factor, when I set each of these equal to 0, I'll get that x equals a positive 1 minus I radical 5 over 2. And from the second one, I'll get a positive 1 plus I radical 5 over 2. Right? Because I would be subtracting, or I would be adding 1 and subtracting I radical 5 over 2 from the first one, and adding 1, and adding I radical 5 over 2 to the second one. And so that would be my answer. Oof, that was a lot. It's okay though. And again, that denominator doesn't simplify, so we're just going to leave it as is. Okay, number B, letter B. So again, every time it says solve, we want to get this to the same side. We want to get this equation set equal to 0. That's our first task. Once we get this set equal to 0, then we can start solving. So like in the last problem, I want to get rid of this 2 out front. So I'm going to divide absolutely everything by 2. So that'll give me x plus 1 squared minus 12 equals 0. Now I have a nice pretty difference of squareds here. So I can say x plus 1, because that's the square root of the first term, plus the square root of the second term. X plus 1 minus the square root of the second term. Let's talk real quick about radical 12. Hopefully we can look at radical 12. We know it splits into 4 and 3. The square root of 4 is 2, and the square root of 3 is radical 3. So I'm going to replace that radical 12 with 2 radical 3, because that's actually the simplified version, the way I would prefer it. Once I get here, I can set each of these factors equal to 0, and I can solve. And when I do that, I'm going to get x equals a -1 plus or minus 2 radical 3. Okay, make sure your answer matches mine when you're adding, and make sure you understand how I got that. Okay, moving on to C. Again, this is not set equal to 0, so that's the first thing I got to do. So I'll get 2x squared plus 8x minus 3 equals 0. So again, we have 3 terms here, so we can always check our little box method and see if that's going to work. So we have 2x squared up in the top left, -3 down in the bottom right, 2x squared times a -3. We want something to multiply to -6x squared, but add to 8x. Sadly, there aren't any numbers that are going to do that. The biggest numbers we can get that would multiply to a -6x would be 6 and 1. Well, even that wouldn't work. But 6 and 1 are never going to add to 8. So we are going to have to, yet again, do new parent function. You're going to get real good at it by the end of this. So we look at the first two, we say, what can we take out of that? We can take out a 2x. When you take out a 2x, this will turn into x, and this 8 will turn into 4 because you took out a 2. Please be careful of that. Then we find our axis of symmetry. So this 0 is 0. This 0 would be a -4 divided by 2. -4 over 2 is a -2. So for our vertex, that is the x value. We're going to plug that back in order to get the y value. So we'll do 2 times -2 times -2 plus 4 minus 3. So it'll be 2 times -2 times 2 minus 3. 2 times -2 is -4 times 2 is going to be a -8. Minus 3 will be a -11. So our vertex is -2, -11. Then we're going to set this up. We'll set it up as x minus h, so minus a -2, that double negative will go positive, squared, plus k, which in this case is a -11. Last thing we have to check is if we have a greatest common factor, or I'm sorry, not a greatest common factor, a leading coefficient, which is right here, that's a 2. So we do need to put a 2 out front to compensate for that. And again, this is still equal to 0. Now we can solve this just like we solved the last one. We'll get rid of that 2 by dividing everything by 2. So we have x plus 2 squared minus 11 over 2 equals 0. So while 11 over 2 is not ideal, it is still split by this negative number, or I'm sorry, this negative symbol. And so that means we can still factor it by difference of squares without having to worry about imaginary numbers. So we'll say x plus 2 plus radical 11 over 2 times x plus 2 minus radical 11 over 2. We set each of these factors equal to 0 and we solve. So we'll get x equals of -2 when you solve this, plus or minus radical 11 over 2. And so that will be our answer. Please make sure you're solving those correctly, going from the factors to the solutions. I know I did some examples of that earlier, but it's just a little tedious to write it every single time. So just make sure you know how to do that. Okay, moving on to the next one. So again, we got to get it set equal to 0. So we'll subtract 3 from both sides to get 2x squared minus 4x minus 3 equals 0. We have 3 terms, so let's check and see if we can do our box method again here. So we have 2x squared in the upper left, -3 in the bottom right. When we multiply those two together, we will get a -6x squared. And we want something that's going to add to a -4x. Oh, we are having some terrible luck today because that, yet again, does not work. Factors of 6x squared are going to be 2 and 3, which won't add to 4. and 6 and 1, which again won't add to 4. So yet again, here we go. Gonna be real good at it by the end of this. We'll do new parent functions. Out of the first two, we can take out a 2x. Be left with x minus, instead of 4, 4 divided by 2 is 2. We'll find that axis of symmetry. This 0 is 0. This 0 will give us a positive 2 divided by 2. 2 divided by 2 is 1. So for our vertex, that is the x value. And we'll plug back in to get the y value. Oh, I'm kind of running out of room. So 2 times 1 is 2, times a negative 1 is a negative 2. Minus 3 is going to give us a negative 5. Okay, we're doing great. So then we can set up this problem. We can say x. Why is my pen writing? I don't know why my pen stopped writing. Give me one sec. So we would write this as x minus h, so minus 1 squared plus k, which is a negative 5. And again, that leading coefficient is 2 equal to 0. Okay, like the previous ones, we'll divide everything by 2. And so that will give us x minus 1 squared minus 5 over 2 equals 0. And again, it's split by subtraction, so we don't have to worry about imaginary numbers, and we will just do our nice pretty difference of squares. So we'll write this as x minus 1 minus radical 5 over 2, or plus, it doesn't matter. And then the other one would be x minus 1 minus radical 5 over 2. We'd set each of these equal to 0 and solve to get our answer as x equals 1 plus or minus the square root of 5 over 2. So that would be our solution. Moving on, let's find out if this one factors. Okay, we're already set equal to 0, which is a good thing. So now, and we don't have any greatest common factors out of 3x squared, 2x, and negative 8. So let's see if we can factor this thing. So we have 3x squared and negative 8 in the bottom right. We'll multiply those two together. So 3x squared times negative 8, we want something to multiply to a negative 24x squared, but we want it to add to a positive 2x. And this one actually does work out quite nicely. It's going to be a positive 6x and a negative 4x, because those will multiply to a negative 24x squared, but add to 2x. So out of the first two, we can take out a 3 as well as an x. Out of the bottom two, since that x term in that bottom is negative, we're going to be pulling out a negative 4. Out of the left two numbers, we can only take out an x, because that's all they have in common. And out of the right two numbers, both 6 and negative 8 are divisible by 2. So this is going to factor to x plus 2 times 3x minus 4. And again, it's set equal to 0. So that's our factoring portion. Now we'll take each of those, I'm gonna draw a little line. We'll take each of those factors and we'll set them equal to 0. So we'd subtract 2 to get that one of our answers is x equals a negative 2. We'll add 4 to both sides to get that 3x equals 4. And then divide both sides by 3 to get that x equals 4/3. And so these would be our two solutions. Yay, moving on. We have f. So again, we're not set equal to 0 yet, so let's get set equal to 0. So we will subtract 50 from both sides to get x to the third plus 2x squared minus 25x minus 50 equals 0. When we have 4 terms, the same way as when we have 3 terms, we can still use the box. Now, we do need to check that there's a greatest common factor, and in this case, there's not, but we always want to be careful of checking for that. So the only difference between when we have 4 terms versus when we have 3 is we'll still put the highest degree term in the upper left, the lowest degree term in the bottom right, but now we actually have what's in the other 2 boxes already given to us. So a 2x squared and a negative 25x. This makes factoring a lot easier. So out of the top 2, I can just take out an x squared. Okay, please note that's not just a regular x. Out of the bottom 2, I can take out a negative 25. And again, I'm making that negative because that x term in that bottom is negative. Out of the left 2, I can only take out an x here because that's the only thing they both have in common. And out of the right 2, I can take out a positive because that x squared term is positive 2. So right now we have this factored to x squared minus 25, x plus 2. But hopefully we notice that we have this x squared minus 25, and that's actually a difference of squares. So we can factor this even further into the square root of the first term, which is x, plus the square root of the second term, which is 5, times the square root of the first term, which is x, minus the square root of the second term, which is 5. So again, that's our difference of squares. And now we are totally done factoring because everything has an exponent of just 1. And so with that being said, we can set each of these factors equal to 0. And we can solve each of them. So when we solve, we'll get that x equals negative 5, positive 5, and a negative 2. Okay, moving on to G. So again, this is not set equal to 0, so we want to get it set equal to 0 first. So we'll subtract 9 for both sides. So we'll get 2x to the third plus x squared minus 18x minus 9 equals 0. Again, we'll check for a greatest common factor, but we actually don't have one here. So we'll move on to using our box method. Highest degree term in the upper left, so 2x to the third. Lowest degree term in the bottom right, which is negative 9, and we'll just fill in the other 2 boxes with the other 2 terms that we have. Out of the top 2, I can take out an x squared. Out of the bottom 2, I can take out a negative because that x term is negative 9. Out of the left 2, I can take out a positive 2x. But because that x to the third term is positive, I'm taking out a positive number there. And out of the right 2, they don't really have anything in common, so I can just take out a 1. So I would write this as 2x plus 1, x squared minus 9 equals 0. And I'm almost there, but again, this x squared minus 9, that's going to be able to factor further because not only do I have a squared there, I don't have an exponent of just 1, but I also have a difference of squares because of those negatives. So I can write this as 2x plus 1, x plus, right, the square root of the first term plus the square root of the second, the square root of the first term minus the square root of the second. And then I can set each of these factors equal to 0 now that I got them all nice and factored pretty. And solve. So I get that x equals a negative 1/2, a negative 3, and a positive 3. And I'm not going to show you that solving step, but that's how you would go about doing it. Okay. Moving on to H. H is already set equal to 0, which is nice. We check to see if there's a greatest common factor, and there's not. But actually, this is a difference of squares again. We can take the square because we have 2 terms, and that's typically a hint when you have only 2 terms that it's going to be a difference of squares. When you have 3 terms, that's going to be your box method, trinomial factoring. And when you have 4, you can again use your box method, but 2 typically means it's just greatest common factor or difference of squares. So the square root of the first term, the square root of 4 is 2, and the square root of x is x. And we would add the square root of the second term, square root of 49 is 7. And then we would do 2x minus 7. That's how it's going to factor, right? Again, we're taking the square roots of that first and that second term, adding them together and subtracting them. And that's how we would factor that. Then I can take both of those and I can set them equal to 0 because the entire thing is equal to 0. And when I solve that, I'll get that x equals plus or minus 7/2. Okay, so moving on to I. Again, first thing we should always check is that we're set equal to 0, which we are. Next thing behind that is to see if we have a GCF. We actually do. We can take out an x squared out of all 3 of these terms. So that will leave me with 4x squared plus 19x minus 5. Now I just have a trinomial in those parentheses, so I'm going to see if I can just factor that piece. I am going to leave the x squared out front. I'm not dividing it out. I'm just factoring all the way down. So I'd have 4x squared and a negative 5. When I multiply those two together, I want something that's going to multiply to a negative 20x squared, but add to 19x. So the two numbers that are going to do that are a positive 20x and a negative 1x. And so that works out quite nicely. Out of the top two, I can take out a 4x. Out of the bottom two, because that x term is negative, I'm going to be taking out a negative 1 because they don't have any other number in common. Out of the left two, the only thing those two have in common are an x. And out of the right two, both 20 and negative 5 are divisible by 5. But that x term is positive, so I'm going to use a positive 5. So again, I'm going to keep x squared out front, and this will factor to 4x minus 1, x plus 5 equals 0. Now I set each factor equal to 0, and one thing that people often leave out is setting this x squared, this GCF we took out in the beginning, equal to 0. Because that is a variable, we still have to set that piece equal to 0. And so when I solve all of these pieces, I'm going to get that x equals 0, a positive 1/4, and a negative 5. And so that should be my answer. So make sure you're setting that GCF, if it has a variable in it, equal to 0. Okay. Moving on to J. Again, we need to get this set equal to 0, so we'll subtract 5 from both sides to get 12x squared minus 4x minus 5 equals 0. And then we'll check to see if we can factor this. So we look to see if there's a GCF, and there's not. So let's see if we can do the box method. So we'd have 12x squared in the upper left, negative 5 in the bottom right. Multiply those two together. And that's going to give us we want something to multiply to a negative 60x squared, but add to a negative 4x. Okay, and those two numbers are going to be a negative 10x and a positive 6x. Okay, so out of the top two, we can take out a positive 2x. Out of the bottom two numbers, they don't really have anything in common, so really we can only take out a 1 there. Out of the left two, both of those have both a 6 and an x in common. And out of the right two, both of those have a negative number in common as well as a 5. So this would factor to 6x minus 5, 2x plus 1. We set each of these factors equal to 0, and we solve them. And when we solve, we'll get that x equals 5/6
and a negative 1/2. Okay, moving on to k. Again, not set equal to 0, so let's get it set equal to 0. So we'll subtract 5x squared from both sides. So we'll get 6x to the 4th plus 13x to the 3rd minus 5x squared equals 0. Next thing we check is to see if it has a GCF. It does. We can take out an x squared and we're just going to leave it out front. So we'll be left with 6x squared plus 13x minus 5. And now we'll see if we can use the box method on that middle piece, on that middle trinomial. Okay, so we have 6x squared and a negative 5. 6x squared times negative 5 is going to give us something that we want to multiply to a negative 30x squared. But we want it to add to a positive 13x. Be careful. A lot of people want to say 3 and 10. And while 3 and 10, one of them would have to be negative. And so that's not going to give us something that adds to 13x. Instead, it's actually 15x and negative 2x. Because those would multiply to a negative 30x squared, but add to a positive 13. So be really careful when you're picking out your factors. Okay, so out of negative 6x squared and 15x, both of those have a 3 as well as an x in common. Out of negative 2x and negative 5, those only have a negative in common, so we'll just say it's a negative 1. Out of 6x squared and a negative 2x, they have a 2x in common. And then out of 15x and negative 5, they have a 5 in common. So again, we'll keep this x squared out front. And this factors to 3x minus 1, 2x plus 5. And I kept that x squared out front because we are, in fact, going to set that equal to 0 whenever we solve. Because it is a factor. And so when we solve, we'll get that x equals 0, a positive 1/3, and a negative 5/2. So please make sure you are solving those. Okay, moving on to L. Hopefully we can see yet again that we actually have a difference of squares here. It looks a little funky, but that's okay. So we'll take the square root of the first term, which would be x minus 4. Remember, it's a difference because it's split by this negative symbol, plus the square root of the second term, which would be radical 32, times the square root of the first term, which is x minus 4, minus the square root of the second term, which is a radical 32. We do need to talk briefly about 32 to see if it's going to simplify any further. And again, you can either do this by the birthday cake method or by just looking at it. I'm going to do it by the birthday cake this time because I didn't last time. 32 is divisible by 2, which would give us 16. That's also divisible by 2, which would give us 8. It's also divisible by 2, which would give us 4. It's also divisible by 2, which would give us 2. And that's also divisible by 2, which would give us 1. So our couples would come out. So 2 times 2, and our single would stay home. This one left over would be. So 2 times 2 is 4. So that will simplify to 4 radical 2. Either way you could have done it is 32 splits into 16 and 2. Square root of 16 is 4, radical 2. Either way you solve it, that's what it should be. And so we're going to write that down, 4 radical 2. 4 radical 2. Then we just set each of these equal to 0 and we would solve them. And so when you go ahead and solve them, oh, my pen keeps dying. Sorry, guys. There's a lot happening right now. There we go. So when you go ahead and solve this, you're going to get that x equals 4 plus or minus 4 radical 2. So that would be our answer. Please make sure you're careful when you're solving that and you're not combining that radical term with that non-radical term. Okay, those can't be combined. That's not how that works. Okay. Okay, now we're going to simplify expressions working with I. So we'll start by adding. And whenever we add, we simply combine like terms. So we'll do 5 plus this -2, which would give us 3. And then -3i plus this 4i, which would give us plus I. That would be our answer. In B, the only difference is we are going to need to distribute that negative before we can do anything. So that would give us -4, and that negative times -2i would give us plus 2i. And then that negative does not get distributed to that plus 3 on the very end because that is not in the parentheses. So we're just going to leave it there, and we'll combine our like terms. So 8 minus 4 plus 3. That's going to give us 7. 8 minus 4 is 4, plus 3 is 7. And -5i plus 2i will be a -3i. So that'll be our answer there. Now we're going to do some multiplication. Okay, so we can use the box method for this if you'd like. You don't have to, but it helps some people. So we're multiplying 2 minus 3i times 4 minus 5i. So 4 times 2 is 8. 4 times -3i is a -12i. 2 times -5i is a -10i. And -5i times a -3i is going to be a positive 15i squared. Make sure to include that squared. So that's going to give us 8. -12i plus a -10i will give us -22i. And then plus 15i squared. Now, one thing we need to note is that I squared is the same thing as -1. So we can actually turn that 15i squared into just a -15. And then we can combine our like terms. So we would say 8 minus 15 is a -7 plus that 22i. So please remember that I is equal to radical -1, but I squared would just be a regular -1. So every time we see an I squared, we can replace it with a -1. And so that would be our answer. Okay, now we're moving on. I'm just trying to see where we're at. Okay, now we're moving on to rationalizing the denominator. So when we have something like this, we need to multiply by the complex conjugate of the denominator. So that means same numbers and the opposite sign. So 1 plus 2i, what we do to the denominator, we also have to do to the numerator. Okay. So I'm going to do my box method for these to make sure that I'm doing this correctly. So I'll start with the numerator. Okay, so 3 minus 7i times 1 plus 2i. 1 times 3 is 3. 1 times -7i is a -7i. 3 times 2i is 6i. And 2i times -7i is a -14i squared. So that numerator will become 3. -7i plus 6i is a -i minus 14i squared. And I'm just going to leave that alone for right now. I'll worry about changing some of those numbers in a minute. Then I'll do my denominator. And I'll get 1 minus 2i times 1 plus 2i. 1 times 1 is 1. 1 times a -2i is -2i. 1 times a positive 2i is a positive 2i. And -2i times 2i is a -4i squared. So I'll have 1. Those I terms will cancel, leaving me with minus 4i squared, which is exactly what I want. So from here, I can turn all of those I squareds into -1s, which would give me 3 minus I plus 14 over 1 plus 4. So I'll combine some like terms. So I'll get 17 minus I over 5, but we want to write this in standard form, which is A plus BI. So A would be 17 over 5, B would be a negative 1 over 5, and we would put the I on the end. So we're just kind of splitting up that fraction. And so this would be our solution. Okay. Now, when we have something like this, it is really, really, really important that we take out i's first, because if we went ahead and multiplied these together, we'd lose a part of our solution. So radical negative 10, I can turn that into I radical 10. Okay. Radical negative 4, I can turn that either, well, it depends on how much you want to simplify it. I'm going to definitely take out an I, but hopefully we know that 24 splits also into 4 and 6. The square root of 4 is 2, and the square root of 6 is 6. So we'd write this as 2I radical 6. Okay, so what's outside the parentheses, we're going to multiply together. So this I and this 2I will multiply together to get 2I squared. And then what's inside the radical will also multiply together. So 10 and 6 will get radical 60. I do need to see if that 60 simplifies any further, which it actually does, because it's going to split into 4 and 15. Yeah, 4 and 15. The square root of 4 is 2. Square root of 15 would just be radical 15. So simplifying this, I'm going to turn that I squared into a negative 1. I'm going to turn that radical 60 into 2 radical 15. And now I'm going to multiply everything outside the radical together. So 2 times negative 1 is negative 2, times 2 is a negative 4, radical 15. And that would be our answer. Okay. If you struggled with that simplification, that's okay. You also could have just taken like an alternate method to doing this would have been to do I radical 10 times I radical 24. So that would have been I squared radical 240. And then simplifying radical 240 from there. So I squared would be negative 1. 240 would simplify into 16 and 15. Square root of 16 is that 4. Square root of 15 would stay the same. And again, that's how I'm getting negative 4 radical 15. Either way is totally fine. You would get the same answer. The biggest part of that is making sure you take out that I. Okay, let's do another fraction. So again, we're going to take this and we'll multiply by the complex conjugate, which will be the same numbers in that denominator, but split by the opposite sign. And what we do to the bottom, we also have to do to the top. We'll use our box method to multiply the top out. So 2 plus I, 5 minus 6I. 2 times 5 is 10. 5 times I is 5I. 2 times negative 6I is a negative 12I. And negative 6I times I is a negative 6I squared. So that numerator will become 10. 5I minus 12I is a negative 7I. Minus 6I squared. We'll worry about the I squareds in a minute. Now let's do the denominator. So we have 5 plus 6I, 5 minus 6I. 5 times 5 is 25. 5 times 6I is 30I. 5 times negative 6I is a negative 30I. And negative 6I times 6I is a negative 36I squared. So again, those middle terms will cancel, which is what we want. And we'll be left with 25 minus 36I squared. Now we simplify. So those I squareds will turn into negative 1s.
And so we'll get 10 minus 7i plus 6 over 25 plus 36. So that will give us 16 minus 7i over 61. That's right. Yes, 61. Okay. And again, we want to write this in standard form. So that's going to be 16 over 61 minus 7 over 61i. Okay. And that should finish us out for the non-graphing portion of the non-calculator section. So now we would move on to graphing. Okay, and now on to graphing. So we're going to start this first one. This one is in this one is in what we call standard form, which is y equals ax squared plus bx plus c. And when we have something like this, the easiest way that we're going to use to graph it is we're going to convert it to the intercept form. So in order to do that, we're going to do new parent function. So we'll take f of x equals x squared minus 6x plus 8. And we're going to figure out what we can take out of the first two, which is going to be an x times x minus 6. And like in previous new parent function examples, we're going to find our axis of symmetry. So in order to do that, we'll get our zeros. So from this factor, that's going to be 0. From this factor, that's going to be a positive 6, right? Because we'd set that equal to 0 and add 6 to both sides. And then we divide by 2. So 0 plus 6 is 6, divided by 2 is 3. So that means our axis of symmetry or line of symmetry is x equals 3. Please make sure you're writing that as a line. And so that's going to be a vertical dotted line through the x value of 3. Now we want to find the y value of our vertex, because remember that line of symmetry is also the x value of our vertex. So we're going to plug that back in. We're going to find f of 3. So we're going to say 3 times 3 minus 6 plus 8. So that's going to be 3 times a negative 3, because 3 minus 6 is a negative 3. 3 times negative 3 is negative 9, plus 8 will give us negative 1. So that means the y value of our vertex is negative 1. So we'll plot 3, negative 1. And then we can rewrite in vertex form. So we can say in the vertex form, y equals x minus h, which we just found to be 3 squared, plus k, which is a negative 1. So it's actually going to be minus 1. And our leading coefficient in the original problem was 1, so we don't need to put any number out front. So this is this equation, but rewritten in a way that's a little bit easier to graph. So now this is taking the parent function points, and we can check that we're applying these transformations to them. So this 3 means we're going to the right 3. And this 1 means we're going down 1. So I'll take all my parent function points and move them to the right 3 and down 1. So that was 1, 1, move to the right 3 and down 1. 2, 4, move to the right 3 and down 1. And then all of those are also reflected in order to give us a graph that looks like this. Okay. Our domain, as always, is the x values. Those are negative infinity to infinity. Our range is bottom to top. So the lowest y value we have is happening right here at negative 1. It is a closed circle, and it's going all the way to the top, all the way to infinity. Now to find the y-intercept, we're going to set x equal to 0. And you can set x equal to 0 in the original problem or in your rewritten vertex form. So either place you want to do it, that's fine. I'm going to do it in the original, just in case I made a mistake on that vertex form. I would do 0 squared minus 6 times 0 plus 8. So this will become 0, this will become 0, and I'll get that my intercept is just 0, 8. And that makes sense because that would be somewhere up here. And it looks like my graph is heading in that direction. In this case, because this graph is opening up, I have a minimum value, and that minimum is the y value of our vertex, which is a -1. And so that's how we would graph that. I'm going to do the other standard form just so that I'm following kind of a similar pattern. So it says background. So this again is another standard form. So I want to get this into vertex form. And this one's going to be a little bit trickier. So we start the same way. We want to convert this into vertex form. So we look at our first two terms. And we say, what can I take out of both of those? So out of both of those can only come an x. And this is where it gets just a little bit not fun. So we want to find our axis of symmetry from here. And in order to do that, we need to get our zeros from this new parent function. So one of those zeros is just 0, but the other one is a little bit worse. We'll have to take 2x plus 3 and set it equal to 0. Subtract 3 from both sides to get that 2x equals a -3. And then divide both sides by 2 to get that x equals a -3/2. Okay, so that's going to be one of our other zeros, a -3/2. And we're going to divide all that by 2. So when we do that, that's going to give us a -3/4. Okay, if you struggle with fractions, -3/2 divided by 2 is the same thing as multiplying, or divided by 2 over 1 is the same as multiplying 1 over 2. So that's how I'm getting -3/4. Okay. So that's going to be our line of symmetry, x equals -3/4. Again, I know it's a little gross, but bear with me. So -3/4 is happening about right here. It does not have to be perfect. In fact, it probably won't be. And then we want to find, because again, that's our x value of our vertex, we want to find the y value. So we're going to plug this back in. We'll say -3/4 times 2 times -3/4 plus 3 minus 2. Okay, I'm going to keep this -3/4 out front. 2 times -3/4 will be -3/2 plus 3 minus 2. Some of us may be struggling a little bit with our fractions. On the test, most of these are going to be fairly pretty. This one just happens to be a little bit less fun. So -3/2 plus 3 is a +3/2. And 3/2 times -3/4 is -9/8 minus 2. -16 minus 9, -25/8. Not fun. Kind of a gross number. So that's going to be approximately a little over -3. I don't know exactly the number off the top of my head, and I don't have a calculator on me. Oh, wait, here I do. Okay. Yeah, it's -3.125. We're just going to go a little bit beyond 3, and we'll plot our point right there. A little bit beyond that -3. Okay. From here, one point that's going to be fairly easy to find is that y-intercept. But before we do that, we're going to rewrite this. So we're going to write this as f of x equals x minus h, which in this case is this -3/4. So that double negative is going to become positive squared plus k. So plus -25 over 8. And then we do double check. Our leading coefficient is 2, so we should be putting a 2 out front here. And so this is our new equation. So it's vertically stretched by 2. It's shifted 3/4 to the left and down 25/8. So this is a vertical stretch by 2. We're moving to the left 3/4. And we're moving down 25/8. Again, these are kind of gross numbers. So a way we can get some prettier points, because sometimes we do want prettier points in this world, is by going back, and we're going to find the y-intercept to help us out a little bit. So we'll say f of 0. I'm going to plug it into the original because it's a little bit nicer for me in this example. And again, this whole thing will go to 0. This whole thing will go to 0. So f of 0 is -2. So our y-intercept we read as a coordinate point. It's going to be 0, -2, which is about right here. And we can reflect that. Please note it is 3/4 away from the axis of symmetry. So we need to go 3/4 on the other side, which would only take us to 1.5. -1.5. Okay. And while we could do the transformations for this, and typically in any other problem we would, because this problem is so complicated, one thing we can actually do is pick an x value that we want to plug in that'll get us an additional point close to that axis of symmetry. So a good point to pick would be maybe 1 or -2, because those are very, very close to the axis of symmetry, and wouldn't be too difficult to plug in. So I'm going to plug in a +1 into the original equation, just so that I have to deal with a few less fractions. And I'll say f of 1 equals 2 times 1 squared plus 3 times 1 minus 2. 1 squared is just going to be 1. So this will be 2 plus 3 minus 2, which will just be 3. So this gave me, in case I needed it, an additional point of 1, because that's what I plugged in, 3, because that's what I got out. And I'm going to plot that. So 1, 3. And then I am going to reflect it, which will be right here, which is -2.53. Okay. And then I can connect all those points and get a graph. So not the most fun graph, but once you can get that intercept, which is probably the most difficult portion, the rest comes pretty simple as long as you're kind of plugging in values around that intercept. But this is why it's important that we're getting that vertex form so that we can identify the intercept and identify that axis of symmetry, and we're not just plotting random points along the way, and we're not certain of where our vertex is. So again, domain is going to be -infinity to infinity. Range is going to be bottom to top. So that's going to be bracket -25/8 to infinity. And we have a minimum value here. And again, it's that y value of the vertex. So -25/8. Okay. I think I'm done torturing you with that one. So let's move on to the next one. So B is in intercept form. Okay, so B is in intercept form. That's in y equals a, x minus p, x minus q. So we want to identify p and q, which are our x-intercepts, because that's going to help us the most. And so in this case, our x-intercepts are going to be opposites, right? Because the original equation is subtraction. So, and you can also think of this as setting this equal to 0 and solving. So x minus 1 set equal to 0 and solve for would give us 1. And x plus 5 set equal to 0 and solve for would give us -5. So we're going to plot 1, and we're going to plot -5 on that x-axis. The nice thing is this kind of gives you automatically 2 points. Then we need to find our axis of symmetry. And the way we do that is we're going to add these two y-intercepts together, or I'm sorry, x-intercepts together, and divide by 2. We've been pretty much doing that all day. So we'll do 1 plus that -5 divided by 2. So that'll give us -4/2, which is just -2. So our line of symmetry is x equals -2.
And this is actually really nice because we can check ourselves. That line should be going straight through -2 and should be halfway between both of our intercepts, which it is. Similar to the last example, we know that -2 is that x value of our vertex, but we don't know what the y value is yet. So we're going to go ahead and plug that back in. So we'll say f of -2, that's what we're trying to find. So we'll keep that negative out front. -2 minus 1, -2 plus 5. We'll do parentheses, so -2 minus 1 is -3. -2 plus 5 is a +3. Negative times -3 is 3. Times 3 will give us a +9. So we're actually getting a +9 here. So be careful with those negatives. So we'll plot -2, +9. So there's a point there, and then it does say we need our y-intercept. So remember, in order to find that y-intercept, we are going to find f of 0, plugging in 0 for x. So that's going to be -0 minus 1 times 0 plus 5. That'll be -1 times 5. So negative times -1 is just 1, times 5 is just 5. So we'll get 0, 5 as our y-intercept because we plugged in 0. We got out 5. And we will also reflect that point to get 5 points on this graph to give us a pretty good shape of what we're working with. So it looks like this. Again, domain is -infinity to infinity. Range is bottom to top, which in this case is going to be -infinity, and it stops at 9. We have a max value in here because it's opening down, and that maximum value is the y value of 9. Okay, and that's 5 points, which is all we really need to get a good graph, so we can continue on. So going on to E is also in that intercept form. So let's start by finding our x-intercepts. So from this factor, we set that equal to 0 and solve to get -1. And from this factor, we'd set that equal to 0 and solve, and we'd get -3. So we'll plot -1 and -3 as our two intercepts, and let's find our axis of symmetry. We'll add those two values together. So -3 added to that -1 and divide by 2. We're taking the average of these. So that'll be -4 over 2, which is just -2. So our line of symmetry is -2, and that's happening right here, as we should expect, halfway between the vertex, or halfway between the two x-intercepts. This is the x value of our vertex. So now let's plug it back in to get our y value. So we're going to find f of -2 to get that y value of the vertex. So we're doing 2 times -2 plus 1 times -2 plus 3. So that's going to be 2 times -1 times a +1, which will just be a -2. So we get the point -2, -2. Oh, and I accidentally wrote it. Okay, so we have 3 points there, but typically we would like to have 5, if at all possible. So in order to get that last point that we want, well, we have to find our y-intercept anyway. So we'll find f of 0. So we'll say 2 times 0 plus 1 times 0 plus 3. That's going to be 2 times 1 times 3, which is 6. So I plugged in 0. I got out 6. So my y-intercept is right here. And I can reflect that to get an additional point. That gives me 5 points. So I can connect these points and make a graph. Hopefully a slightly better looking U than that. Maybe if I used a thicker pen, I don't know if that would make it better or worse. Yeah, both better and worse. Okay, don't know how that's physically possible, but we'll move on. So domain, as always, is -infinity to infinity. Range is bottom to top. So in this case, it's starting at a -2 and going to infinity. And this is going to have a minimum value because it opens up. And the minimum value is the y value of -2. Okay, we've been through 2 forms so far.
So now let's go through the last one, which is consequently the first one we ever learned, and that is vertex form. So vertex form, which is this one, is in the form y equals a x minus h squared plus k. So the easiest thing to find from vertex form is consequently the vertex. It's the opposite of what's in the parentheses, so -1, comma, the same as what's on the outside, so -7. So -1, -7 is our vertex. And our line of symmetry will be the vertical line going through that vertex. So x equals -1. Okay, so that gave us some information. The way that we can think about this is this transformation. So again, this is going to be a vertical stretch by 2. We're moving to the left 1, and we're moving down 7. So that's one way to think about it. Another way to do this is we do still need to get our y-intercept. So I'm going to find f of 0. So I'll do 2 times 0 plus 1 squared minus 7. Sometimes it's nice to also perform the transformations and then plug in 0 as a check to see if you've done the transformations correctly. 1 squared is going to give us 1. 2 times 1 is 2 minus 7 is going to be a -5. So I plugged in 0 and I got out a -5. So this point will be right here and I can reflect it. Again, if we took that original point of 1, 1, vertically stretched it by 2, that would be here, and then moved it to the right one, to the left one and down 7, we would still get 0, -5. So you can also do it as transformations. Either one of those is okay. I'm going to do my next point as transformations. You also could pick the x value 1 or -3 and plug it in to get an additional point. But I'm going to do this one as transformations. 2, 4 is where I would start in my parent function. I'd vertically stretch it to 2, 8. And then I would have to move it left 1 to 1, 8 and down 7 to 1, 1. Okay, and again, I can reflect that point. If you don't believe me that that's correct, you also could have done f of 1. You could have plugged in that x value of 1. You would have done 2 times 1 plus 1 squared minus 7, which would be 2 times 2 squared minus 7. We do the squared first because of PEMDAS. So 8 minus 7 is 1. And again, you would still get the same point of 1, 1. So either way, you can get the same point and get enough points in order to get a good solid looking graph. We like to have 5 points because when you only, oh God, if only this would look like a curve. Sorry, y'all, I'm shaky. I don't know why. Pretend that that looks like a decent looking U. God, it looks like a really bad U. Okay, pretend it looks decent looking. My brain lost it for a second because I got so upset over that. The reason we want to have 5 points in our graph is because when you just have, say, 2 or even 3, you can often confuse what's meant to be a U shape with what's meant to be something linear, because typically 2 points denote a linear graph, or absolute value graph is denoted by, say, 3. So when we have a quadratic, which is what we have here, we want just a few more points to make sure we're really getting that curve correctly. Because again, if I only had 3 points, say I didn't get these top points here, I can make my graph look like this, which isn't right. I mean, I don't know, I could even do something funky like that, which isn't quite right. So we want to make sure that we have enough points to get a pretty decent idea of what the graph is going to look like. And typically 5 will give that to us. So domain again is negative infinity to infinity. Range is bottom to top, so that's going to be a -7 to infinity. And we have a minimum value here, and it is -7. Okay. And on to the last problem in this section. So again, this is in that vertex form. So we want to find HK. So opposite of what's on the inside. So that's going to be a +1. Same as what's on the outside. That'll be a +3. So 1, 3. Again, our line of symmetry will be through that vertex. So x equals 1. Okay. So from here, we can also talk about transformations. So this is a reflection over the x-axis. This is a vertical stretch by 2. This is left 1. I'm sorry, this is right 1. I don't know why I'm losing my mind tonight. Right 1, and this is up 2. So again, if you want to do that with a parent function, you can. So let's say I do it with the next point that I have. Okay, so I know that in my parent function, I get the point 1, 1. I'm going to reflect that over the x-axis to get 1, -1. I'm going to vertically stretch it by 2 to get 1, -2. And then I'm going to move it to the right one, which would be right here, and up 2, which would end up, oh, where did I mess up? I think I messed up somewhere. Let's try it again. Sorry about that. Okay, try it again. I have the 0.11 on my parent function. Okay, I reflected over the x-axis to get 1, -1. I vertically stretch it by 2 to get 1, -2. Oh, I know where I messed up. I wrote up 2. This is +3. In the original problem, it's +3. Okay, so I vertically stretch it by 2. I move it to the right one, and then I move it up 3. And so this should be the final point that I get. And I would also reflect that over the x-axis. If you don't believe me, you can plug in 2. Just to check my y-intercept, I am going to still plug in 0. So I'd say -2 times 0 minus 1 squared plus 3, which is -2 times -1 squared. Remember, because of PEMDAS, we're going to do that exponent first. So -1 squared would become a +1. And -2 plus 3 is 1. So I just confirmed that my y-intercept is 0, 1. And therefore also the point 2, 1 exists. Again, if you wanted an additional point, you could plug in another x value. Good options would be 3 or -2 or even -1. All of those are kind of close enough to the axis of symmetry that you could get a good point. But let's say I wanted to continue with the transformation. So I have the point 2, 4. If I reflect that over the x-axis, I would get 2, -4. If I vertically stretched it by 2, I would get 2, -8. And then I want to move that to the left one to get 3, -8, and move it up 3 to get 3, -5. And so I can get rid of all these little transformation points, and that would be my final point. Again, if you really want to check it, you can do f of 3, which would be 3 minus 1 squared plus 3. So it's going to be 2 squared. Which would be -8 plus 3, which is -5. And that's exactly what I got. and then I can reflect it. So whether you feel more comfortable plugging in or whether you feel more comfortable performing the transformations, I'm fine with either, as long as you are identifying that axis of symmetry and that vertex from the original equation and finding that y-intercept. So then I have 5 points, which is enough to get a halfway decent looking graph. Maybe if I could draw a straight line, it would be. Oof, oof. Okay, it was all right. So domain is negative infinity to infinity. Range is bottom to top, so that's going to be negative infinity, and it's stopping at the y value of 3. And in this case, we're going to have a max, and it's going to be a positive 3. Okay, and that will cover graphing. And now this video should jump over to me working on the calculator section. Okay, hello everyone, this is Mrs. Hubbard, and you probably already watched the beginning of this video, but we are going to do the word problems separately so that I can show you via a calculator. So starting with question number 7, at the yearly firework display, a rocket is launched into the air with an initial velocity of 95 feet per second from a platform that is 8 feet above the ground. So this is the formula we have. So what is the function st that models the height of the rocket at any time t? Let t represent the number of seconds elapsed since firing, and st represent the height of the firecracker in feet. So basically, we're going to use this formula right here. So I'm actually even going to copy and paste it. And insert an equation. So we're saying the height, which is s of t, is equal to negative 16 t to the second plus that initial velocity, which if we go back to our question, it says the initial velocity is 95 feet per second. So we're going to be adding 95 feet per second. So I need to multiply that by time. And then it's saying it's being launched from a platform that is 8 feet above the ground. So that 8 feet above the ground is telling me that my initial height, my HO, is going to be 8. So this would be our setup for that problem. So the next thing it says is how high is the rocket after 1.5 seconds? So be sure to show your setup. So we're going to take that equation we just wrote, and we're going to use it here. Okay. But instead of t, we're going to plug in 1.5 because we're looking for what is the height at 1.5 seconds. So everywhere we see a t, we're going to plug in that 1.5. So now it sounds like a good time to jump over to our calculator. So we'll go over to our little calculator. We're going to hit graph, and we'll hit tab in order to type in the equation, which we said was negative 16. Instead of t here, we're going to use x. But x squared plus 95x plus 8, and we'll hit enter, and we'll let it graph. Okay, not a great graph, but we're actually just looking to trace. So we're going to go to menu, trace, and we'll click graph trace. And from here, we can just type in 1.5 and hit enter, and it will tell us what our output is, which in this case is going to be 115. So we'll go back to our problem. And we know now that this is going to be equal to 115. Right, so what does that mean? We're going to write a little sentence. The rocket is 115 feet high after 1.5 seconds. Okay. So that would be an adequate setup, and then we could use the calculator for that. So then it asks, when is the rocket 100 feet above the ground? Is there more than one answer to this question? Explain your answer and show your setup. So again, we're going to use that same equation we've been using. Okay. And if the rocket is 100 feet above the ground, then in this case, instead of replacing t, which stands for time, we're going to replace s of t, which stands for that height. So we're going to replace that with 100. Okay. What we can do here, I don't know if I can get it to line up nicely, but what we can do here is, in order to solve this, we want to get this set equal to 0, right? That is our goal. So because it's going to be really, really difficult to figure out where the graph is at 100 exactly, right? Even with tracing, it can be very hard. So the easiest way to do this is get our equation set equal to 0, and then it's pretty simple from there. So we'll subtract 100 from both sides. And so when we do that, that'll give us that 0 equals negative 16t squared plus 95t minus 92. Right? Once we get here, since we're set equal to 0, we can look for the zeros on a graph. So let me just explain that one more time. Again, rocket height was 100 feet above the ground, so we set this equation equal to 100. But finding 100 in a calculator when that's the y value is a little difficult. So instead, we're going to get it set equal to 0 by subtracting 100 from each side. And now we can use our calculator to solve. So I'm going to have to change this equation. So I'm going to hit tab, and then I'm going to click the up button to get back to my equation that I had. And this time, remember, instead of plus 8, it's going to be minus 92. And we'll graph it. So again, and not super clear to see. So maybe we hit window and we click back to our standard window. Okay, that's a little bit easier, especially because here we're no longer looking for just a random point. We're looking for the zeros, right? Because we're looking for where this graph is going to be equal to 0. So we'll click menu, analyze graph, zeros. We'll go to the left of the first 0, to the right of the first 0, and it gave us our first one. And we'll repeat that process for the other one, because there are 2 zeros here. And that gave us our other 0. So even though this 0, the number is 5.82 times 10 to the negative 11, that's close enough to 0 that we'll be okay with that number. So we have it happening at 1.22 and 4.72. So let's go back. So it says, when is the rocket 100 feet above the ground? Right? So we'll say the rocket is 100 feet above the ground at 1.22 seconds and 4.72 seconds. This happens because the rocket achieves this height on its way up and again on its way down. Right, because we're dealing with a parabola here. So as our rocket goes up, it'll hit 100 feet, and then as it goes down, it will hit 100 feet again. Again, it's starting at 8, so it makes sense that it's happening twice. Okay, how high does the rocket go? When does the rocket reach this height? So again, we're going to take that original equation, not the one we changed in the last problem, that original one. Okay, and we're going to go to our graph. And if we are looking for how high the rocket goes, that means we're looking for the maximum. I don't know why mine is in Comic Sans right now. We're looking for the maximum, which occurs at the vertex. So what we're really looking for here is the vertex, right? So let's go over back to our little graph. We'll change this equation one more time. So we'll hit tab and then up, and we'll change this back to a +8 and graph it. Again, not a great graph, so I'm going to maybe zoom out. or we can always change the window. Either one of those is fine. Just to real quick get a little bit better graph. Ooh, this is going pretty high. Okay, but then I can kind of see my whole graph. And then again, not a great window because we are zoomed out pretty far. So it may actually be wiser to go window, zoom, window settings, maybe -10 to 10 on the X values because I don't have a whole lot. And then maybe we say we go up to 200. Then we'll just click OK. Okay, that's a little bit better graph. I can see things happening a little bit easier. I'm not so far spread out, not a great axis, but I can see the whole graph from here. So again, make sure you're practicing getting a good window to see the entire problem. So now I want to figure out how high this will go. So I'll hit Menu, Analyze Graph, and Maximum. I'll go to the left of the maximum, to the right of the maximum, and it gives it to me right there. So my maximum is the y value of this vertex, so 149. And that's happening at the x value, so at 2.97. So the maximum height is, sorry, I just forgot it, 149. So 149 feet. And this happens at 2.97 seconds. 2.97 seconds. Okay. And the last question of this one, when does the rocket land? Be sure to show your setup. So when the rocket lands, that means that what we can do is take this equation that we've been using this whole time, and instead of setting it equal to a number, we're going to set it equal to 0, right? Because setting s of t equal to 0, which is what we're doing, setting s of t equal to 0, which is equal to that equation, because we're saying the height here is 0. Change this role. So what we want to find here is the zeros, but of that original equation. We don't need to find the 0 on the negative side because we can't have a negative time. That's not the way the world works. Instead, we want to find it on the other side. And I'm going to delete this even though I know it's already there, just to show you guys how I would find that. So I go to Menu, Analyze Graph, I click 0. Again, left side of that 0, right side of that 0, and there it is. We're getting, again, 5.82 times 10 to the negative 11th, but that's close enough. So this is occurring at 6.02 seconds. So we'll go back to the review, and we'll say the rocket lands at 6.02 seconds. And that's how we would solve that one. Okay, moving on to number 8. Answer each of the following questions. Be sure to set up for each equation. A ball is thrown upward from a 270-foot cliff with an initial velocity of 80 feet per second. Write an equation. So again, we're going to take the same equation we've been using for the last two. We're going to plug it in there. But this time s of t is equal to negative 16t squared. It's saying this one has an initial velocity of 80 feet per second. So we're going to put 80 in for that VO, that initial velocity. And it says it's thrown upwards from a 270-foot cliff. So we're going to make this plus 270. And so that will be our equation. So this asks, is the ball on the way up or on the way down at t equals 4? Well, there's a couple of different ways to do this. The first way is to figure out where the vertex is, and then you can kind of figure out whether the ball's on the up or on the way down. Or instead, you could just hop over to your graph Again, I'm going to hit tab and up to change this equation. So this will be 80x and then plus 270. And I'll graph that. Okay, not a great window, so I'm going to hit menu, window settings. I'm going to give it a little bit more height. Doesn't really need more in the axis. Oops, still not enough. Just for safety, we'll go 350. Oh, still not enough. Okay. So sometimes you have to mess around with these axes in order to get one that's going to give us a nice little graph here. So this is asking whether we're going up or, sorry, I want to delete these so I can show you how I'm getting them. Okay, so this question is asking whether we're going on our way up or on our way down when time is 4. So all we need to do in order to figure this out is we're going to hit menu, we're going to hit trace, graph trace, and we're just going to type in the number 4 and hit enter. So we can see right on our graph it's happening here, and that's headed on the way down. So we'll go back. Okay. The ball is on its way down because it has already passed the vertex at 4 seconds. You could also say it has also passed the maximum height. Okay, and that's true. That is what has happened. Okay, so then it says, when will the ball hit the ground? So again, like in the previous problem, what that means is when will the height be 0? So our setup is going to be using this equation, but instead of s of t, we're going to be setting this equation equal to 0. Okay, and so we're taking that equation and we are setting it equal to 0 in this case. So we're trying to find the zeros here. So we'll go back to our graph. Again, we're not changing this graph. I don't need to find this -0 because I can't have a such thing as negative time. So I'm just looking for that positive 0. So I'm going to hit menu, analyze graph, 0. I'll go to the left side, I'll go to the right side, and it'll give me this 0 right here. Again, that y value is close enough to 0 that it's okay. And it gave us 7.31. So we can go back to our problem. And we would say the ball will hit the ground at 7.31 seconds. Okay, so then we have how high is the ball after 1 second. So if we want to find how high the ball is after 1 second, we're going to take that equation, and instead of t, we're going to plug in 1. Give me 1 second. So everywhere we see a t, we're plugging in 1. And you can either type this into a calculator, as long as you keep the parentheses, you should be all right. Or we can just hop on back over to our graph, hit menu, trace, graph trace, and type in 1 and hit enter. And it'll give us that value is 334 feet. We'll go back here. Right, so we just found out that this is equal to 334. So we would say the ball is 334 feet high after 1 second. So then it says, when will the ball be 300 feet above the ground? Be sure to include setup. So we'll set up the same way using the same equation, but this time we want to know where our height. Okay, I'm going to enter so I can. Okay. But now we're going to set that height equal to 300 because that's what we want to know. We want to know where will the ball be 300 feet above the ground. So this would be our setup, but this isn't quite good enough because we want this to be equal to 0 because again, finding a y value exact as 300 is a little bit difficult, but finding something that's equal to 0 is not too bad because it's pretty easy to calculate our zeros. So we're actually going to subtract 300 from each side in order to get a new equation. And so when we do that, we should get that 0 is equal to negative 16p squared plus 80 minus 30. And this is what we're going to go back and plug into the calculator because now we can use this new equation to get some zeros. I'm going to hit tab up, and now I'm doing minus 30, and I'm graphing that. Okay, so now we have a new graph here. It looks shifted down, which is essentially what it should look like. And now we want to figure out where this ball is going to have its zeros. And its zeros are technically where it's hitting 300 feet, okay? Because we've shifted this down 300 feet. And so that's how we know that these zeros are occurring. So we're going to hit Analyze Graph, 0. Go to the left and to the right to get our first 0. And then we'll again hit Analyze Graph, 0. Left of that 0, right of that 0, and we'll get another one there. So again, this is actually hitting 300 feet twice, similar to the last problem, and it's happening at 0.408 and 4.59 seconds. Okay. So the ball will be 300 feet above the ground at 0.408 seconds. And again, at, I forgot what the number was, 4.59. This font is really driving me crazy. Okay, and so that is what that question would look like. And finally, we're asking, what is the maximum height the ball will reach? Again, last time we're going to use this equation, but we're going to take this equation and we're going to talk about how the maximum occurs at the vertex. We do need to change our equation in our graph back to that original, right? The one that's no longer shifted down 300 feet. So I'm going to move this back to a plus 270. And I want to find the maximum here. So I'm going to hit Menu, Analyze Graph, Maximum, to the left of the max, to the right of the max, and there it is. 370 feet at 2.5 seconds. But this didn't ask us when it occurred. So the maximum height is 370 feet. And make sure you're including units when you type this out. We started with feet, we need to end with feet. Okay. Here we go. So Old MacDonald has an apple orchard. There are 30 apple trees in the orchard. Each tree produces 500 apples. For each additional tree planted in the orchard, the output per tree drops by 10 apples. The orchard can support no more than 50 trees. The X is the number of trees that Old MacDonald should add. Express the total apple production as a function of X. Whoa, that's a lot of stuff. Okay, so let's start by just thinking this out and writing just like kind of a word sentence to help us process in our brain what's going on. So we know the total apples is going to be equal to the number of trees times the production of the trees. Okay, so we know that. So Old MacDonald has an apple orchard, and there are 30 trees in that apple orchard. So we'll say A as a function of X, okay, apples as a function of trees is going to be equal to, okay, so we know we're starting with 30, so we'll write that down, okay? And we're multiplying that. It says each tree produces 500 apples. Okay, so that's to begin with. So 30 times 500. Okay, that's great, but that's not really a function. But this is saying, starting out, there are 30 apple trees in the orchard, and each one produces 500. So for each additional tree planted in the orchard, so for every X that we add to the total number of trees, the output per tree drops by 10 apples. So from 500, we're losing 10 apples for each one of those trees. So this would be kind of our starting point for an equation like this. If we wanted, I'm actually going to write it as an equation real quick. Okay, so we'll say A apples is equal to, we just said 30 because that's our starting point, plus the number of apples times 500 minus 10 times the number of apples. Okay, we can either leave it like this, or if we did our little box method and distributed it out to get a function that looks pretty in standard form, we would get negative 10x squared plus 200x plus 15,000. Okay. Whew. And that would be our equation. So either one of those I would accept, whether you left it in that factored form in the first one or whether you distributed it out in the second one. Both of those would work just fine. And when you type in a new calculator, either of those would work as well. Okay, so it says, what is the domain for the problem situation? So we're talking about what are our possible X values. Well, we know that we're starting with 30 apples in the tree. So, or I'm sorry, 30 apples in the tree, 30 apple trees. So we know that the domain is 0. And it could include 0. So I'm going to do bracket 0. And then it says the orchard can support no more than 50 trees. Well, if we already have 30 trees, then that means we can only add 20 more. So the domain is going to be 0 to 20. Okay. And again, that's because we could not add any trees to this orchard, but we cannot support any more than 50. And so 50 would be our max amount of trees we could have, which means we could only add 20 more to the original 30. So how many additional apple trees should Old MacDonald add to maximize the production of apples? Well, let's go ahead and graph this. And so I'm going to put this equation away. And I'm just going to put this in as factored form to show you that we can, in fact, type it into our calculator as factored form. So 30 plus x times 500 minus 10x. And it'll graph that. Oh, it disappeared. Oh, where did my graph go? Sorry, guys. I have no idea what just happened to my graph. There it is. Okay. Sorry. Forgot. We're going to get a lot of apples. I'm going to zoom out a bit more. Tell me this would stop. Ooh, okay. I'm going to change the window here. Mercury. Sorry guys, I'm just messing around with the window, and you're allowed to kind of mess around with the window as well. See where you want. It's still not going to be great, but it's a little bit better. That's okay. So what we're looking for here is we're going to be looking for the maximum. And we can see that it's kind of occurring here. So we're going to hit Analyze Graph. We're going to hit Maximum. We know that this is probably to the left of our maximum, and this is probably to the right of our maximum. And so we have that happening right about here. So that is happening at 10 additional trees. And so that's going to give us the greatest output possible at 1.6 times 10 to the fourth apples with 10 trees being added to the orchard. Any more than 10 trees would cause us to decrease in our production. Any less than would not give us quite enough. So we'll go back and we'll say he should add 10 trees. To maximize production. And again, you could use this for any maximum. So whether we're trying to maximize area, whether we're trying to maximize production, anything like that, you will always be able to look for the maximum happening at that vertex. And so that should finish us out for this review.